All right, so this is part two of the Bridge Designer software tutorial. So far, I've shown you how to open it up, how to load a template, and how to create a rough bridge. Now what we need to do is start shaving some cost off of our total. Now, the bridge must function, and the goal is to get less than $200,000. To toggle back and forth between the test screen and the build screen are these two tools. This one will bring you to the build screen. This one will bring you to the test screen. Most of your work is going to be done in the build screen. You're also going to want the member list, which is toggled right here. Now, in the other video, we looked at the difference in color of each piece as it was being tested. This member list over here gives us more detailed information about the forces acting upon each piece. So if I select the piece in the table, it's going to identify where that piece is in the bridge, and it's going to tell me what type of material. This piece is carbon steel, CS. It is a bar versus hollow tube. It is 200 millimeters by 200 millimeters, 4.47 meters in length. Slenderness, we're going to skip that for right now. We'll come back to that later. This piece has 0.31 of force to strength. If this number exceeds 1, this is a ratio. So if this number becomes greater than 1, that means there is more force than there is strength, and then that piece will fail. This component has no tension acting upon it. All right, those are really important. To get this bridge to operate for less than $200,000, you will need to evaluate each piece individually and probably more than once. So I'm going to show you what it looks like when the bridge fails. So if we take our component, actually it'll be easier if we'll take component 39 here. It's right in the middle. That's a really important piece for the bridge. We're going to decrease the size of component 39 to 110 by 110, and we're going to test the bridge again. Now, this bridge doesn't even hold its own weight, and it fails. The truck doesn't even try to drive across. If we go back, the program is going to show you that the piece broke. It's highlighting it with the blue marks, which tell you it broke due to tension. And then if we look in our table chart, here you can see that that ratio is greater than 1. As a matter of fact, this one's closer to 2. It's 1.83. So we know that there is more force than that piece is strong. So to get your bridge to function for less than $200,000, what we're really trying to do is make this ratio as close to 1 without going over as possible. That means our bridge is working as efficiently as it possibly could. So in a perfect world, these would all be 0.99. Now, you're not going to be able to get them to all be 0.99, but you want to increase that number to get it as close to 1 as possible. Some of these components may be under 2 different forces. If we look at 23, this is a good example. This one has both compression and tension. Now, those forces aren't significant because that piece is pretty large, but it does have both forces acting upon it. There are not many pieces that have that, but there are a few that do. Typically, those are the pieces in the middle. When the truck is on one side of the bridge, that piece will be under tension, and as the truck gets to be on the other side, it will transfer to compression. And you'll need to know and pay attention to that. If the bridge breaks, what you need to do is fix the bridge, and this one is 0.83, so I'm going to go back. We were at 200 before, so I'm going to go back to 180, and we're going to test our bridge again. Now, you don't actually need to wait for the truck to drive across the bridge. You can toggle back, and it'll tell you if it was successful or not. And this one was. Now, my ratio is at 0.69. So we could actually make that piece a little smaller yet. Now, when I make these pieces smaller, it's going to decrease the price of the bridge. And this is critical to getting the bridge to function for less than $200,000. Now, as we decrease the size of that piece, we're also eliminating weight of the bridge. So that means that the stress on all of the pieces around that component gets lessened. So what you'll have to do is work your way through, decrease the size of each piece as much as possible to eliminate as much of the cost. Now, that's only one of the factors. You're also going to have to use hollow tube where it's appropriate and solid bar where it's appropriate. Now, there is a help section, and in the how to design a bridge, it's going to give you a lot of information. And on the bottom, it tells you solid bar or hollow tube. I would suggest you pay very close attention to what it's telling you right here. That will tell you where you need to use solid bar versus where you need to use hollow tube. So you can make those adjustments by selecting the piece, modifying its material type, and now it's a little bit different. If we click here and find that same component in the table, you can see that component number 6 now is not bar, it is instead tube. If we were to test that bridge, we can go back. That piece failed pretty dramatically. It was almost 4, so I would need to increase the price or increase the size of that piece so that my bridge functioned again. When you use hollow tube, you will need to use bigger pieces, but it's still going to be cheaper than the solid bar in certain areas. And again, follow the help menu. There, the truck got on the bridge and then it failed. So I'll need to, I'm at 1.01, so this is about as close as you can get without it actually working. So if I increase that size one more time, the truck will, in theory, should make it all the way across. And it does. All right, so the size of the piece, whether it's hollow or solid, the type of the material is probably the trickiest. Save that piece for last. Before you evaluate what type of material, I would tell you to use all carbon steel. Make sure all of the appropriate pieces are hollow tube versus solid bar, and then shrink each component as much as possible, decreasing as much of that price as you can. Work your way on that, and then once you have all of your pieces shrunk, the pieces that are still really large in size, like this piece is 400 by 400, those are the pieces that you're going to want to consider using a higher strength so that you can potentially shrink the size even more. When you add that strength, you can see the price right now is $574,455. When I go to the more expensive material, it jumps to $577,000. So it is significantly more expensive, but what that's going to let you do is decrease the size. So now I'm at 573. If we test it, it works. So now I'm using a more expensive material, but I was able to shrink the tube, so I'm still saving overall. So use those points. Use the help and the how to design a bridge to help you work through that. And that's all good information. I do want to show you one other thing that you may run into. Sometimes students try to test a bridge that is not structurally sound. I deleted this piece completely. If I were to try to test this, it's going to give me an error message, and it's going to say the bridge cannot be tested. If this comes up for you, pay attention to what it's saying. It's giving me this error message. This truss is unstable because a highlighted panel is rectangular rather than triangular. Without that cross brace, the bridge would shift and it would fail. So if you get this error message, that means that there's something wrong with your bridge. So if I drew that piece back in there, it would let me test that. So good luck on your challenge. Work carefully. It's kind of a tedious project, but typically students enjoy the process. So good luck.